Thank you again. And my second paper again is related to my own setup, hybrid source desalination system. Here I am developing a coupled thermal network electrical circuit for the Peltier device in heat pump application for the same desalination system. These are the outlines for this presentation work. And again, I will highlight the main findings of my research work in this presentation is I'm developing a model, and this model is of electrical and thermal also. And we are optimizing this performance for the enhanced heat pumping capability so that I can integrate this Peltier model again within this analysis system. The previous talk was about the surface temperature measurement, but this is about the heat pumping capability of the Peltier model, because same we can do means the Peltier model is like a generator also, it's like a refrigerator also if we give a reverse of that. And novelty of my finding is the coupling of thermal model and the electrical model. And the thing is, this novelty is precise and efficiency, because I'm just focusing about the material perspective, thermal capacitance by the material also. And the impact of this is in emergence, energy efficiency and scalability. Scalability means I can attach 2, 3, 4 Peltier model either in series or either in parallel, so that one model can be used for anybody. And the relevance of this work is you will find an advancement in non-conventional desalination system, not a kind of conventional, because we can use this desalination system as in a home as a prototype also. And of course, practical application, like if we use this model for the neck cooler, usually you are seeing for the neck cooler in the arid region kind of things for the Peltier. And another thing is we are using in the incubators for the heating and cooling applications. People are using this Peltier module. This is the solar state. People are using for the condensing the steam in the solar state. People are also using this Peltier model as a thermal generator. And there is a lot of literature also about the network method of electrothermal analogy for the thermal and the electrical part. And some model explain deal with through the SPICE circuit simulator or using analog behavior model, where they are using the analogy between the cause and effect, which is the causing and what are the effects, like voltage and current is there, and forces mass means what is causing and what are the effect. Based on that, you will have another case. And this was the paper which I presented. Which have written in this paper means I got to find that to work this Peltier model at higher coefficient of performance, I need to work in this region, and you will see a very large range of current and coefficient of performance is depending on this. And this region is giving an optimal performance, whereas this region is giving for high gain of ratio for my desalination system. Therefore, we need to switch between these two. If we need to between these two, we need to have a model which is coupling this Peltier model with my desalination system. Therefore, from the point of view that the thermal model of the desalination system can be easily translated to electrical network system for heat transfer, a model is developed with circuit perspective based on physics of operation, because I need to go inside the physics of the material. From the physics of the material, I need to develop the circuit which will exactly match the model of the Peltier model. And the thing is also we need to have a stability of minimum temperature difference with the variation of current, which I explaining in this diagram for the latent recovery system. So I started how to do the things. I will start go from the physics of the Peltier model step by step. This is like a Peltier model with the pellet thermal element, where this is the cold junction, this is the hot junction. If you give a power supply to this Peltier element, due to Peltier effect, heat is transferring from the cold junction to the hot junction, and this is called the Peltier effect. Another effect is happening due to the flow of current is the Joule's heating. Again, further, due to the temperature gradient, and the flow of electrons, there is also a heat diffusion kind of thing. This is called the Thomson effect. And obviously, if the internal in the previous slide you have seen also in the previous presentation you have seen the connection between the Peltier element with the copper strips, which is showing the also the internal thermal conduction due to this. And we have along with that we have a hot ceramic surface where which is giving a mechanical strength to them. Here also the thermal conduction is happening. Therefore, there must be heat taken outside also. We need to consider all those things. And the reverse of this Peltier effect is the Seebeck effect, which I am not explaining. I am not using this effect. And this physics is explaining all that about the Peltier model. I need to use all this physics to develop my circuit. Therefore, this is the Peltier lake of the Peltier model, where this is N type and P type, and this is the spatial variation and the temporal variation for this one, this Peltier model. From the previous physics, which I explained that if you give a temperature difference, a potential can also develop, and if you give a potential temperature difference can happen. It will give a two model, like I need to have, it will be a electrical model also, and it will be a thermal model. I need to develop both the sub model for that. Now approaching to the thermal model, I just explained in the previous part at the junction, Peltier effect is happening, which due to one effect in heat is absorbed and one due to other effect heat is released. Which is explained here, the internal temperature can also, yes, the thing is that here for modeling, I need to have a node always, because the node is giving the measurement. Therefore, this is the internal temperature node we need to define, and this is external temperature node where the ceramic surface are there. Now, again, I am going to the control volume x plus tx where it was there. And if you go in the internal of this x plus tx control volume, this distributed network, you can see that this distributed network where this I need to define in the electrical domain. Therefore, this will be acting as a current control source due to the flow of current through the material, and this is the again the current control source due to the temperature dependency coefficient, because due to the temperature difference and the material non-homogeneity, this effect is coming out. Again, the thing is, I am developing this for the control volume. This control volume, I need to have a distributed network. Therefore, I am joining these two at center node, where also if flowing energy is flowing from x to x plus tx, it is also storing the energy. Therefore, one capaciting element, mass capacitance is also I found for that. This term is showing the steady state source term, and this part is showing the transient state source term. Again, going further from the elemental cross section of the Peltier module. To visualize in the previous section, I was just showing that from the mathematical point of view, how can visualize these kind of things. If you dq, we can write dqx plus dx, and in these terms, all three terms are there, where the first term is relating this one, and this term is relating Thomson effect. Again, if you take the analogy between dq and I and voltage and temperature, you can see that this CTH thermal capacitance is like an MCP, which is shown here. From again, I need to, from the distributed network, I need to go to the lumped network so that I can integrate the lumped network to the thermal network. So this one is the from distributed to lumped network, where I am separating this for the cold junction and this is for the hot junction. And these are the current control source for heating and Joule Thomson effect. And owing to the symmetrical structure, and just my assumption for this is that the hot side and the cold side are symmetrical. And thermal capacitance is dedicated to cold side and hot side. This is MCH by 2 and MCC by 2 for the lump network. But the thing is that Thomson coefficient is very low compared to other part, because Thomson coefficient will be in nanovolt per Kelvin, where the Seebeck coefficient will be in a millivolt per Kelvin. Therefore, we can neglect this Thomson coefficient. Therefore, ignoring the current source term offered by these terms, we will get this model. From this will create the thermal submodel for me. Again, you will see this two these two ground term. This ground term is showing that if I am taking ambient as a reference, then it will give a bipolar nature for the voltage in the electrical domain. I need to have one unit domain reference voltage for the electrical one. Therefore, I am developing for the one I am considering 0 Kelvin as a reference. If you consider that this is the final thermal model for my Peltier model. From the after developing the thermal model, I need to develop the electrical model, and this electrical model can be developed from the electrical characteristics, like considering the voltage, current, and the load for the power generation. And again, we have to consider that temperature difference is creating a potential. And we need to have a temperature is acting as a voltage node for the Peltier module, as is shown in the previous slide. This will be make a electrical submodel for the Peltier model, where this term is like a voltage controlled voltage source for the electrical resistance, and this is for the electrical resistance which depend on the thermal model. Now, after developing electrical model and thermal model, I need to couple this electrical and thermal model, where the temperature distribution from the thermal submodel influence the electrical performance, and the current flowing through the electrical submodel influence the thermal aspects. Therefore, if you build both, you can see that if you give the potential, difference, output will be a temperature difference. If you give the output input as a temperature difference, output will be the voltage. Therefore, it looks like heating cooling. Heating cooling is one output, and potential development is another output. It looks like a three-port network. And if you couple this three-port network, it looks like this, where the thermal submodel. This is the thermal submodel, which must sense the current flowing through this device and sensing the current through the feedback loop between the electrical and the submodels. Further, for my application, I'm doing for the heat pumping application, I am giving an electrical supply. Therefore, I'm just again reframing this previous model for electrical one and defining the flow of electron and current in terms of current source and the resistance, and defining these two parameters for the ceramic surface, the RC network for the ceramic surface. This will be the final. Now, again, the thing is, I develop the model, I need to validate this with the simulations, and after that, the experiment. This model I developed, and what I did that I am giving a heat sink lower to the, and I am giving a thermal mass where I am giving a cyclic heating source to see that if we give the current to this current control, it can track the current temperature or not. Based on that, I need to have a sensor for that this one and give the set point temperature for that. Suppose that we are giving to work at a 5 degrees Celsius, it should, whatever the inputs, it should track and come to the 5 degrees Celsius. And another parameter, external parameter I consider is the ambient, because ambient is also going to vary. After measuring these two parameters, this temperature is going to the feedback for the voltage source. And from this, I designed a controller, and controller is giving a feedback to the current source and again giving to the Peltier module. This is the whole developed model. in the simulation. And for this simulation matter, I just consider this parameter, which is the practical value I consider for the PEC 12706. And this is for the temperature measurement, which I shown in the previous slide by this one. And I defined a controller parameter KP and can. Why this is I developed by using a small signal model, which I have in this paper. Now, if you see the result that if you're giving a cyclic source of heating, I need to tightly couple this one. If you zoom it, if you see it, that the temperature, set temperature is the green one. The cold temperature is following this one, even if this cyclic heat is changing. And this is happening with this current applied in the feedback. And for the source of variation, I'm just giving this ambient source variation also. Again, to prove it, I have also developed this current controlled part of this and temperature sensor of part of this to again do this. And this is the assembly, Peltier setup assembly, where I have done the experiment to see that how tightly it's measuring the temperature. And in the conclusion, means I developed the thermal submodel and electrical submodel, and again did the coupling for that so that I derived the three-port network. And the thing is, our focus was on developing the thermal capacitance, which in the literature people are neglecting. Because of this, neglecting this thermal capacitance, we are not getting a great accuracy in set temperature. And the beauty of this model is that again, we can scale this model, means I can connect in the series or a parallel kind of things, and we can integrate with this thermal system. And again, this experiment setup for the verification I have developed also. I did the experiments. In the future, I will just complete it for the work. And these are the reference. Thank you, Tom.
Any questions? Thank you so much.
Okay, thank you.
I think we can have a break now. Yeah. We have Dr. Bashir is not present, so we can have a break now. I don't think it's worth starting another paper, and we will run over the coffee break. So, coffee break now. Okay, guys, back in 3-4 minutes. Thank you.
The screen recording is still going on. Should I
I can handle this. Yeah.
you can handle?
Yeah,
Thank
thank you. Thank you. Nice presentation.
Yeah.